Recording. Yeah. So clock. Let's understand in a few simplified version. Every digital processor works based on the clock signal. This signal is a continuous stream of electrical pulse. Right? What are those signals? Every microcontroller use these signals. What is the signal? 0 and 1, high and low. Right? That means if signal is going up, down, up, then down. Signal is going up, then down. That this is the pulse. We call whatever we can call it, signal, pulse, high, low, right? So one complete high plus low cycle. That means when signal goes up and down, then it's called one cycle. We call it clock cycle, right? That means this is the one single step for the CPU. CPU will execute one step in that much of in single clock. Okay, इसको हम बोल सकते हैं ये होती है माइक्रो कंट्रोलर माइक्रो प्रोसेसर की बारीकी, कितने कम टाइम में एक सीपीयू एक क्लॉक साइकिल एग्जीक्यूट कर सकता है, ठीक है, और कितनी कम टाइम में वो क्लॉक साइकिल एग्जीक्यूट हो सकती है. ये होती है परफॉर्मेंस हर एक माइक्रो कंट्रोलर की. ये जो होता है रैम रोम, राइट, किस टाइप से गेमिंग पीसी या फिर जीपीयूज जो भी होता है, राइट, कि कौन सी चीज़ कितनी जल्दी फास्ट काम कर सकती है. एवरीथिंग डिपेंड ऑन दिस क्लॉक्स. So the faster clock runs, the faster microcontroller can perform operations. For example, STM32 का जो होता है, let's say it is सभी माइक्रोकंट्रोलर का होता है. लास्ट टाइम हम डिस्कस किया था कि अलग अलग STM32 का कुछ होगा, ES32 का कुछ होगा. कि let's say STM32 का है 72 मेगा हर्ट्स. दैट मीन्स 72 इंटू 10⁻6 मेगा हर्ट्स. मेगा का कितना होता है 10⁻6. दैट मीन्स 70 कितना होगा ये 7 करोड़ 2 लाख या आई थिंक 7 करोड़ 20 लाख क्लॉक साइकिल एवरी सेकंड. ठीक, क्लॉक साइकिल एवरी सेकंड, एक सेकंड में 7 करोड़ 20 लाख तक वो टिक्स, मतलब इतना बार हो जाता है, मतलब उतना क्लॉक साइकिल जनरेट होती है. सो द रिलेशनशिप बिटवीन द क्लॉक फ्रिक्वेंसी एंड टाइमर इज वेरी. क्या क्या फार्मूला होता है दोनों के बीच में? दोनों एक दूसरे के यूनिप्रोपोर्शनल होते हैं. F इक्वल्स टू 1/t और T इक्वल्स टू 1/f, राइट. तो अगर टाइम, लेट्स हम टाइम ले लेते हैं, दैट मीन्स सेकंड, मिली सेकंड, माइक्रो सेकंड, नैनो सेकंड, कुछ भी टाइम ले लेते हैं. सो T इक्वल्स टू 1 डिवाइडेड बाई फ्रिक्वेंसी. व्हाट इज द फ्रिक्वेंसी? दिस वन. एंड इफ यू डिवाइड इट बाई, if we complete this calculation, it would be near by approx something around 13.8 nanosecond. How much? Nanosecond, not millisecond, not microsecond, nanosecond. ठीक है, उस लेवल पे CPU काम कर. दैट मीन्स CPU कैन परफॉर्म एन ऑपरेशन रफली एवरी 13.8 nanosecond, right? So what is the timer actually does? Timer is essentially hardware. It's like a counter. Whenever we are hitting some kind of edge or some kind of high signal or some kind of pulse, right? So our timer is continuously recording that, like 1 0 1 2 3 4 5 6 7. This is the pulse that we are counting every time. So every time a clock pulse arrive, the counter increase by 1. हमने इसके अंदर करते हैं कोड के अंदर +1 वेरिएबल प्लस, राइट. And we are also getting a microsecond from the Haltix function, right? So those are the overall over surface, what we can call like a surface level calculation. But behind that there is a lots of things that is going to happen in nanosecond, microseconds, right? And when counter reach a specific value, the timer can trigger an interrupt, right? Why timer we are using that? Right now we have just completed this part. Like I have given one assignment that count the make a counter up to 10 and then reset the, right, in which we are blinking the LED, right? So in the same manner what we are doing, we are counting the 10, then taking one action to resetting the timer, right? So in the same manner we can also take the different kinds of action when our timers get completed. We can trigger one interrupt, right? That we have done this thing, interrupting the trigger recently, but that time we have generated the interrupt by using the push button, not from the timer, right? We will generate the interrupt through the timer in later workshop. Okay, but we can do lots of things while trigger the action through the timers, like triggering the interrupt, generating PWM signal, toggling the pin, triggering the ADC conversion, start direct memory access transfer. So there are different kinds of things that we can do with the timers. Okay. Now, the timers, especially in STM32, are divided into three different categories according to the requirement of the pulse and actions. Right. There are basic timers. The basic timers known for the timer 6 and timer 7. Right. If you open the cube MX, you can see there is option timers, timer 1, 2, 3, 4. Right. These are the timers available in our specific this controller. Okay. So in other controller maybe there are more than 4 timers. So basic timers are like timer 6 and timer 7. They are simplest timer. It is used for 16-bit counter, programmable pre-scaler, periodic interrupt generation and DAC trigger support. Right. क्या लिमिटेशन होती है इन सब की? नो इनपुट कैप्चर, जो कुछ क्रिटिकल टास्क होते हैं, राइट, जो इनसे हैंडल नहीं हो पाता है, वो इनको नहीं कर पाते हैं. और वो टास्क आर लाइक इनपुट कैप्चर, PWM सिग्नल कैप्चरिंग and no external channels for these timers, right? So they are mainly used for simple time based generation, like you can use in the timer to generate interrupts like these things. Then generate general purpose timer 2 5. These timers are much timer 2 to 5, yes, time, that means timer 2, timer 3, timer 4, timer 5. These timers are much more flexible. Features including like 16-bit counter and 32-bit counter, up to 4 independent channels. This timers have inbuilt sub channels, right? We can use for that different along with this timers. Then it can use to generate the PWM signal. It can use to capture input signals like ADC and output comparison and encoder interface. These timers are commonly used for PWM motors, motor control, measuring the signal frequency and generating the waveforms, right? Then when advanced control timers, timer 1 and timer 8, only 2 timers. These are especially designed for motor control and high precision applications, right? You will see, you will lots of time when you will develop any industrial application on the basis of motor or frequency or waveform generation. You will see the difference, actual difference between the Arduino and ESP and STM32, where we want a good amount of accuracy, and that we can get only through controlling this kind of things, right? There's a dedicated timer for high accuracy precision. Mostly, let's say if you are designing the robot, right, and in the robot we need control over the PID, right? PID, we are using the PID control. So in that time we have to control motor very accurately, right? So in that case we can use this kind of advanced control timers, right? So additional features like include complementary PWM outputs, dead time insertion, break input protection and advanced synchronization. Okay, they are typically used in brushless motor drivers, right, inverter system and power electronics, because those applications are very critical, right, and very fast application where we need to control everything in very microsecond or nanoseconds, right? The core of every timer, time base, right? Every STM32 timer contained a time base unit which determine how time is measured. This unit consists of 3 important registers, right? That means how we are calculating, because frequency is too much high, right? How we are counting at that much of level. So clock, prescaler, counter and auto reload, right? Let's understand each one. The prescaler, what is prescaler? The prescaler divide the incoming clock frequency, right? Why it is necessary? Because the system clock is extremely fast. System can't calculate this much of number, right? Because if it is going, if in 1 second if system will go to count that much of number, definitely it will be completely filled and with the memory in very minimal time, right? So that's why we use prescaler kind of like for the quantization or kind of sampling. You can understand in the perspective of that the similar thing you will see in a ADC type, right, where we have analog signal, we are quantizing the signal so that we can pick only the required signal, right? So here prescalers like it is dividing it is dividing the frequency by a desired number. Let's say we can take here 7199 0 to matlab we are counting from the 0, that's why. So it would be something around 7200, right? When we divide the 72 megahertz by the 7200, then it would be something around 10 hertz, right? So now counter increment every 10,000 time per second, right? We can't increment the timer at that much of speed, but here we can count at least when the frequency every time reach cross 7200, right? Then we will count per second. That means here 10,000, when our clock cycles will continuously goes that much, and it will be divided by that much, and when the result goes at this stage, then we will count 1 second. So I hope you understand the value of 1 second now, how it is coming from heart of the controller, why 1 second is important for the controller, right? So the controller counter register will store the current time value. Example 0 1 2 3 store in the register. That means there's storage wala register, not that current limiting wala register. Okay. Each clock ticks increase the counter by 1. Timers can operate in multiple mode: up counting, down counting, center line counting, and most basic application for up counting, like from 0 to higher level. Auto reload register, what is that? We call also ARR, right? The auto reload register define the maximum counter value, right? Let's say when counter will reach at this peak, right, then it will again get reset, right? At this moment the timer generated event interrupt, the event will generate interrupts, DMA transfer, and peripheral synchronization, right? It is something like we can we can especially it is used for the interrupt generation, right? That we have done the similar thing right now कि आप 10 तक count करो and फिर 0 पे चले जाओ, right? So in the internal side, auto reload register will do the same to generate the interrupt, that whenever the counter will reach at that much of state, 10 second or 12 second or 50 second, whatever, then it will goes to reset. It will clear that register. Okay. Then golden time formula is like this, but I think I am also unable to read it, right? Frequency timer, PSR scaler, we will see that everything when you open that your MX. There is one thing that we still didn't touch it till now: clock configuration, right? And to understand this thing, we have to good enough knowledge about the first of all timer, because these things already, it's everything about the frequency and the clock sources, from where we are getting the clock sources, what are the 64 32, right? How we can change this, what is the divider value 22 or by 1, right? So these are the formula that we are discussing here as a theory part, right? But we'll discuss everything practically also. So if we take one example, generating a 1 second interrupt. So let's say our time clock is 72 megahertz, then we choose a free prescaler to around 7200. Then now country frequency will be 10 hertz, sorry. If we calculate the ARR to generate 1 second delay, we need 10,000 ticks, right? This is the 10,000 ticks, right? And this is our ARR that we have set, right? Now result interrupt every 1 second. How? Because what is nearby? It is nearby 10,000, right? When we divide that when we divide our what we call it, the result of that I think this formula should be okay. When we divide this 10,000 by error, then it will equals to 1 second. Okay. And why timers are important? Timers are like definitely mostly it is 80 to 9% every peripherals that we are dealing with in embedded system, it completely depend on the timers. So whatever it's your communication protocol, it may be your hardware peripheral out actuators like motors, LED buzzer, or input sensor, everything these are depends on the times, right? Whatever we are going to use, let's say if we use the UART, there should be a data speed. Every communication protocol has its data speed, right? Every communication protocol has its format, right? And how these things will be continuously monitored by the CPU, it is completely driven by the timers. Got it? Any doubt in the timer? So this was the general purpose timer, right? Later on we'll discuss how what are the timer inside that STM32, right? How we can use the frequency, how we can change the frequency. We'll see that, and then we will have one complete project over the timers, along with the interrupts also, how we can generate the interrupt through the timers. Okay.